In this video, we'll look at two articles. The first one is about how standing waves are present in flutes, and the second one is comparing different flutes through standing waves. For the first article, the main experiments were done on a wooden 1867 system flute by Rudal-Cartier. Through Lissajous figures and interpolation, it is identified that exact pressure nodes don't exist. In Figure 1, A triple prime produced by normal fingering is sharp-sounding harmonic. The F prime, A prime sharp, and A prime holes are distant enough from the antinodes to considerably raise half wavelength for the appropriate frequency. Procedure in Figure 1 was used for normal fingerings of notes. These notes are produced with help of vent holes and some variant fingerings. Tables 1 and 2 show the results for normal fingerings. In Table 1, a note that's in italics means its note hole is open. Bold means its note hole and all those below it are open. Based on ladder rule, E triple prime, B triple prime, and C4 primes are exceptions, but unimportant. The chart that's printed suggests that the D prime sharp hole be closed for them, but closing or opening has negligible effect. Table 1 shows the distances of observed antinodes from the lower end of flute. Antinodes that exist but not investigated are indicated by X. Inside brackets, figures show positions of antinodes. These antinodes are nearly insignificant in figuring out music note produced. These antinodes mentioned above have another name, parasitic. The musical insignificance is shown because all three notes in which they occur aren't affected in pitch. Timbre if the foot joint, where the parasitic antinodes are removed. Parasitic antinode is one where intensity of standing wave has been reduced significantly by sound energy being radiated. In most cases, the distinction between a parasitic and a significant part of a wave pattern is pretty sharp. Last standing half wave of A triple prime sharp is one borderline case from Figure 1. This half wave, the energy is significantly less than the upper part of the wave pattern, because with many open vent holes, it just couldn't be otherwise. The half wave can be removed by opening the D prime sharp hole. When this happens, the transition from one mode of vibration to another is clear. However, the two modes give out notes that are close to exactly the same pitch and not so different timbres. Table 2 calculates the distance of vent holes from corresponding antinodes. D double prime and D double prime sharp are second harmonics with sole antinode vented, and D triple prime is third harmonic. Two slight exceptions. The distances are all positive. Effect on stability is usually neutral, beneficial, due to adding to fingering on flute a supplementary vent a bit above an antinode. Effect is often destructive if adding a supplementary vent a bit below an antinode. Relative stability of different modes of vibration for a given hauling is the important thing. Part of asymmetry of the effect of the relation between vent hole and its antinode on stability is based on tendency of supra-antinodal vents to be nearly nodal for most likely unwanted modes of vibration than infra-antinodal vents. However, there may be a part that is an asymmetry in the effect on absolute stability. In normal fingerings, for all notes except for A triple prime sharp on the experimented flute, vent holes stabilize desired mode of vibration and correct flatness. A triple prime sharp is the only sharp-sounding harmonic among normal fingerings. Among haulings matching with normal fingerings, there's one sharp-sounding harmonic, which is C5 primes. Variant fingerings given for Bohm system on flute include a good many that are sharp-sounding harmonics. Notes of acceptable intonation have small proneness to sharpness, can be rectified by embouchure. However, they have poor quality. In given distance between antinode and vent hole, proportional change in frequency doesn't depend on the position of the hole. Now to the second article. Baroque, classical, and modern flutes comprise of more and bigger tone holes. We're going to see some reports regarding measurements of standing waves in boards of instruments, frequency dependence of propagation of standing waves in lattices of open tone holes, and compares them with cutoff frequency. Some methods that they used were measuring impedance, standing waves, and pitch. And in the end, the conclusions that they come up to was cutoff frequency of instruments increases with increasing diameter of tone hole. Above cutoff frequency, standing waves penetrate strongly past open tone hole. In the case of instrument with smallest holes, standing waves above cutoff frequency are tiny bit affected by open holes and are close to expected resonances for complete length of instrument. With all tone holes closed, the increasing cutoff frequency gives larger number of impedance minima that are in approximately harmonic ratio with larger holes. This is expected to contribute to production of brighter and louder notes. Below cutoff frequency, standing wave propagates past first tone hole by an amount that gets bigger with frequency and decreases with increasing diameter of tone hole. For cutoff frequency and weakening in the tone hole lattice, observed values match with those of simple empirical model.